maybe just a quick round intro. I'm Daniel, this is my colleague Andreas. Before we start, I'd like to actually ask you a question about this software architecture. Have you ever, who of you has been in touch with Civil tools for the architecture verification? You can just raise your hand. Okay, so I need to explain that a little bit. Maybe as an introduction, can you just go for the agenda slide? Thanks. So about us is now very brief. What we want to have as a background is we do static code analysis. That means we are looking at C, C++, C#, and other languages source code. So we don't execute the code. We analyze the source code and derive a lot of information from the source code without executing it. That's the main story on one side. The other thing is that we use this information to verify this against your software architecture. To this end, just the next question to you would be, are you already using some software modeling tools like UML tools, stuff like that? Can you just raise the hand roughly? Okay, many more. So I give a little bit of an introduction to the architecture verification in a very simplistic format from me, and Andreas is going to the details, starting with software architecture, which is in essence boxes and arrows. So the story behind that is we are usually doing, after doing this code analysis for architecture, you start with boxes and arrows. When you have a new colleague, he or she is hired and you want to explain the structure of your software system, you start with boxes and arrows. And on that level, let's start with that. Now we need to jump to the right one. Let's go to a very simple system with boxes and arrows as an architecture. So let's imagine you start developing a new software. We have a very simplistic architecture with 3 layers, something like down here in the C, that's the hardware abstraction. You have some temperature sensors. A level above is the middleware, where you communicate with different other components. And on the top, in this A box, we imagine the user interface with Qt, for example. That's the beginning of our new product and project. So let's start with the implementation of this. For example, just use your normal C code in code. Now, starting with the boxes and arrows, now you have the code. And imagine that the product that you want to ship is now almost ready, and your product manager comes along and says, we need the prototype tomorrow at the trade fair. I want to present it like in the demo. So it doesn't need to be really productive. It doesn't have to be perfect, but I need something that I can demonstrate to my customers. And just let's assume that the one person who's doing the middleware box, so this B is just not here, he's on leave. So what's to do for making your product manager happy is usually just do a workaround. So just this zigzag line is what you put into code, but you don't see it in the architecture. So you now have the architecture that says we have 3 layers. The code says something different. And what's the problem here is, well, actually nothing. As long as everything goes right, you can go with that product to your trade fair and demonstrate it. The downside is the vision of the code and the code itself are somehow different now. And that's something we call erosion. So it adds complexity and you don't see it. So story continues, your product manager comes back from the trade fair and says to you as an architect, well, it was successful, we now sold it, but you see, we have degree Celsius, but now we haven't sold it to the US where they use degree Fahrenheit. So as an architect, this change is simple. We keep the hardware abstraction as is. We build in some sort of conversion from degree Celsius to Fahrenheit. Who knows this formula by heart? I don't, so you probably have to look it up, and something with 32 degrees. And then implementation continues. You put the conversion into this middle layer. You have the conversion from degree Celsius to Fahrenheit, and then you start you start with the testing phase of your project, and then you start from bottom up, the unit tests. We could use our Squish Cocoa test center to cover that. We find out that both the hardware abstraction works and the middleware also works. And at the very last stage, you do a full system integration test, and you find out that your temperature somehow goes wrong because it's alarming you at 32 degrees Celsius instead of Fahrenheit. So, question to you, how can you fix this? And you have to release your software tomorrow, so you don't have time to dig into your source code. Any proposal? Say again? Yeah, that's the standard way of doing it. They just found out that this conversion works. We have tested it, so why not copy it? That's a real life example. That's not something that just happens. Now we have even more erosion. We have now architecture violations in here. So the architecture says things that are just not true. We have duplicated code, and we will have the next talk from Rainer Koschke about also clones. Now this is a somewhat difficult situation. You don't have the time and fix it. And this is just version 1. So imagine this goes on for several iterations, then you end up in a pretty mess. Now the basic idea of this architecture checking is if we have these boxes and arrows, let's make that a little bit more machine readable. This is now a very simplistic model. Again, the three boxes, 2 arrows on one side. On the other side, we already analyzed the source code, so we know all the dependencies between the components. And now the very simple trick is it's like on transparency paper. So you put those architecture things on one transparency paper. The next layer is your code. You match it, and then you find out by just using the code analysis what's right and what's wrong. So you can do that every time when somebody changes code, commits the code, then you can rerun this analysis, and we can then now check the results. So between A and B, in our architecture, we say A is allowed to talk to B, B to C. And we found something in the source code that says, yes, you're allowed to do that. And there's some deviations because we have a dependency between this A and C that was not allowed. And then we can alert that and report it back to the users. Now, you need to take action on those alerts, and it's basically 3 ways of handling with it. First thing is architect is right and the developer should change their code. That's removing the deviation. Second option would be, even as an architect, you cannot foresee everything. So the developer might be right and you should just update your documentation. Or we accept the deviation for the time being and know that there is something, but we don't actually take the fixes now. Pretty much 3 cases, again, as a graphics. First one, we changed the source code. So our model is now, again, back in line with the code because we fixed the code. The second case is we updated the specification. So we're now granting access from A to B, from A to C, and we know it, and it's still in line with the code. And the final version is, the deviation is there, and we can at least report the analysis results that there is a dependency and there's no more surprises. And that's pretty much the basic idea that we want to go now a little bit further. This was now boxes and arrows by drawing. Drawing could be anything like a case tool or just the simple modeling. And exploring that in practice also means that there could be something like architecture as code. And that's now my point to hand over to Andreas. So no longer just drawing, but also specifying architectural rules that can be verified automatically in your source code. Andreas, you're
okay. Thanks, Daniel. All right, so let's jump into a little bit more tactical stuff. We have seen now the overview, what architecture is, what architecture verification is, what we actually think architecture is, and architecture verification. And now I would like to take you with me to an approach. How can we actually do this in practice? Yeah, how can you model your architecture in a certain format that is lightweight? And you see here there's already the term architecture as code. We go a little bit more into detail into that. Maybe a few of you have already heard this beautiful term. And we will also see how you can use such an approach to maintain your architecture in your project, for example, and to use it as a base for architecture verification to actually check whether your architecture corresponds with the stuff that is happening in your code, as we have seen before. You see, it's a cooking recipe, yeah? So we have only 3 ingredients here. So bear with me. We need 3 things to actually do architecture verification, and we will go through each of these ingredients. So the first one, this is not the first one. This is like the kitchen, yeah? So what we have here now is a small example project. It's mainly C, but it could also be C++, C#. C is very nice because it's very simple, yeah? So we have a project, it's called Engine Control System, but don't look too detailed into the code. This is really just for learning and for tutorials. But what we have here is you have certain kind of source directories, a directory app, engine control, hardware, I/O, a file system and display also. And somehow this is our project. Maybe it's your project or you inherited it from somebody and you would like to have, of course, an architecture because you want to know what is actually going on. What are the eternal truths in there? Yeah, how are things working together? So let's try and build an architecture model for this little project and verify it. So the first ingredient that you need is actually a model, yeah? I think all of you agree with that. So we need somehow these boxes and arrows that Daniel already mentioned. We're talking about static software architecture. Architecture is a broad field, but this means component and dependencies between these components. Here we have a very simple example. We have 3 components, A, B, C, as we have seen already in the example. Yeah, A is able to access B, B is able to access C. But it's beautiful, but where does this architecture model come from? How can you model it? And a few of you already use tools to describe such architecture models, such high-level designs of your code. And there are many ways to do that, yeah? So some people use Word and PowerPoint, and I think we agree this is difficult to use if you want to automatically verify something with a tool, yeah? So if you have a Word document that says, well, this is my architecture, this is a little bit difficult. Maybe AI can generate an architecture out of it, but I never tried it. I think this is not a good idea. So maybe a little bit better idea is to use an architecture-based tool, an UML tool that some of you maybe already know about. Of course, I also have to mention the Axiom Suite also has a modeler tool that can actually draw these boxes that we have seen already in the screenshots. These tools, for example, Enterprise Architect, Rhapsody, there are many, many more. These are great, wonderful tools. So these UML tools, you can do beautiful things with them, a lot of things. But this often is also a problem because you have a large complexity in these tools if you want to model with them. And you also have to learn a new tool now, yeah? And these tools, they really have some kind of a steep learning curve, yeah? You have to do something to model in there if you want to model in a correct way. You see here a few screenshots. All of them actually are architectures of this engine control system, yeah? And the thing is, these also have some kind of a proprietary file format normally. Maybe it's XMI or in XML-based format or even a binary format, yeah, where you cannot look directly into it. So the thing is, how can you actually work together on such a model, yeah? And how can you diff it? This is often a problem, yeah? If you have a change in your architecture model, how can you actually diff it and look what has been changed in my model of my system? So is there a simpler way to maintain architecture and verify architecture models? Well, there is, and this will be the main point of this talk. Yeah, this is one way that we see is more and more popular also among our customers. And this is the architecture as code approach. And this is a very fancy word for something very simple. The idea is now architecture as code means specify an architecture model using a human-readable format. Yeah. Actually, for example, use an approach where you actually really code your architecture. And this is what we would like to introduce to you. In our example, you can actually use a domain-specific language which is based on Python. So you write your architecture in Python. Yeah. So this is the idea. So you do not have another kind of language. If you use Python already, you can actually use Python to express information about your architecture. So there's a Python framework that allows you to specify such models in a very declarative way. You already have seen this ugly thing over here. I drew it last night, I think, with Microsoft Paint. Yeah. So let's say this is the first thing that you come up with. Your colleagues say, well, this is actually something of a high-level architecture of this engine control. I have some kind of an app component there. I have an engine control actual component. I have I/O stuff. I have a sensor, but I have also hardware. And I do not like the app to actually access hardware directly. It should go through one of these layers, for example. Yeah, this is a very, very simple thingy. We will see a little bit more complex example later on. So if you have this beautiful image, we can actually do something like this. You can have a Python script. So this is really an excerpt of a Python script. You have some kind of imports. If you do not know Python, it does not matter. So it's very, hopefully you can also understand it without knowing Python. You can here write something like, I want to have a new architecture. It's called Arch here. And you see here, we just write architecture, then the name of the architecture, and then the components. Yeah. So this is the first step. And you see here, these components, the names just coincide with these things that you have here on the right side. We have here also something which is called component with interface for the hardware. We come to this in a second. For right now, just treat it as a normal component. So, and how can you write this? Well, these are just classes in Python. Yeah, this is very simple. It's just a special kind of class that is provided by the framework for architecture and for component. This is what we can see here on the next slide. And what you can do now, Python is great. Python is wonderful. You can write, for example, in this framework, something like this. App is equal to arch.app. Yeah, of course, you can use this kind of this dot notation here. The framework allows this to say, well, I want to do now something with this part of the architecture, which is called, which is this app component, yeah, that we did before. So because we have now the actual components, but what we do not have yet are the connections between them. Yeah, and this is now the next step. And in this framework, you can write something like this. You have a depends on predicate or depends on method, and you can write something like this. App is equal to arch.app, as we've seen before. And then you can write app depends on arc.engineControl, arc.io, arc.sensor. These are exactly these three edges, of course, that we see over there. Yeah, you can say this is actually my dependency. And you can do this, actually, we will see this later on, in one Python file, in a separate Python file for example, the component app. Yeah, this is one part of your system. So actually, you could also do this for every component. Yeah, you have here, for example, 5 of these Python files, and you can write this kind of information about your architecture in these Python files. And the nice thing is now, if you have your source code organized in, for example, directories, and every directory is one component, you can just check this in with your source code, and you have something that you can read and you can discuss with your colleagues. And you do not have to open another tool. You can use it in your IDE, yeah, and actually do something about the architecture and maybe change it or add some dependency. This is beautiful. Yeah, it's Python. Yeah, it's if you do not like Python, it doesn't matter that much. It looks almost like its own language. Yeah, so it's a very simple format. Yeah, but I like Python, so this is why I'm really happy about this approach here. And you say now, well, I do not use Python. I use plant UML. I use C4, something in there, and I specify or I use something else. You could also say I use JSON. This is all fine. We see here later on why it is a nice thing to use Python, because we have then a good connection to the architecture verification feature, where we check actually whether this is what is actually going on in the code. But what you can also do now, since you have this now in Python, you can access this architecture as some kind of a data structure. And it's very easy to write some kind of an exporter if you want to have a nice visualization of your architecture model, for example. Yeah, you can use an exporter for dot or graphics, for example. This here is, for example, the exporter that our own tool, our internal Axivion tool, for example, produces for this little architecture. Yeah, so you see, it looks way nicer than my wonderful picture in MS Paint. Yeah, but this is not the only advantage of actually doing that. We see this in a second. Let's do a little interlude. The second ingredient is actually the code model. So we have now an architecture model. Great. But now we need also information out of the code. Yeah, and here I keep it brief. So Daniel already mentioned a little bit what we actually have to do here. Here is how when static analysis comes into play. So we have a tool that analyzes the source code, or there are static analysis tools out there that analyze source code. And for the approach of architecture verification, you need also the information from the code in a graphical representation. And you see this down here. You have another graphical representation of your code. These are, for example, source code files, and these are functions, for example, or classes. And you see here edges between them, for example, calls. Yeah, this function calls this function, yeah, or this class actually uses another class. So this is information you have to somehow get through a static analysis tool. And such a tool can transform this into what we call a code view, yeah, or a code model. Yeah. So now we have like two graphs, and somehow we want to see how they actually correspond with each other. Yeah. Where does this code model come from? Yeah, I already mentioned it. This is actually what static analysis does. And it's not only actual calls. I just mentioned calls before, but what you can see here, for example, we have a function print, we have a function status display, and this function status display here, it prints actually speed. Yeah. So if we look here on the right side, this is what the actual result is of a static analysis tool. Yeah, this is a screenshot from one of our tools. You see here status display refresh is this function, again, this red rectangle, and there's a blue line to the print function. This is actually this one here. Yeah, so you have here this information, but you have also a line to the speed. This yellow thingy here, this shape indicates that this is a global variable. A very bad thing to do, but here there's a global variable, and status display refresh actually accesses this, and it does this. Yeah, and of course this is valid and useful information for the architecture check. This is what you want to know. What are you actually accessing? Yeah, but it's not only calls. It's also other things that are interesting, using types, etc. Yeah, and what you also see here is we also have here the information in which directory the actual things are stored in your source code. Yeah, we will see in a second that this is very useful if we come to the third ingredient for the cooking recipe. Yeah, which comes right now. We have these two graphs now. Yeah, we know now how we can get them, but now we have to somehow combine these two things. Yeah, because you have here ABC, but what does this actually mean for your code? Yeah, you have to have a translation from this code information to your architecture information, and this is done by a mapping. Yeah, you somehow have to say these parts of my code in my code model belong to this component. Yeah, and the same here with B, and the same here with C. So this is now something, even if you have used something like this architecture as code approach already, if you have modeled this already, what you normally, I do not think, have modeled in your architecture representation. You have not somehow a direct, clear mapping from your code parts to the actual components in your software. But for actually checking this automatically, this is crucial. You have to have this in some way. And where does this come from again? Yeah, so where do we get this ingredient? If you use architecture as code, you actually can use, again, some kind of an additional function, which is called mapping. So you actually, we add here in this framework a mapping abstraction that just says, well, I have information about this code to architecture. Yeah. You see the usage already here. I think this is clear. App is equal to arc.app. You know this already. So we, again, want to actually say what kind in the code, what kind of elements belong to this app component. And you see here, I hope you can see it, how you can use this mapping. Yeah, you can say add mapping. And then you say, well, everything in this directory belongs to up. And this is then translated. And this information is then used later on in the architecture verification. But it's not only directories. You can also say, well, I have these two files lying around, and I think this is legacy. Yeah, this is, often with customers, yes, this is still there. There's still 5 files. We haven't moved them yet because it's a pain to move them. But technically, from the architecture, they belong to this component or something like this. Yeah, so I'm sure not in your code, but there are a lot of people there where this does not correspond. So, for example, it doesn't have to be directories. You could also actually use classes here, namespaces. Yeah, there are a lot of things. It's just for simplicity here to use this. But here you see the appeal. You can actually have this explicitly given in a text file, in a Python file. And actually also your colleague can look at this and see it already here that this is actually part of this component. Yeah. Sometimes you can even maybe get this out of other things, out of your build system or something like this, yeah, this kind of information. And one thing that I just want to mention briefly, I do not want to make it too, we have said we have these boxes and we have these arrows. This is nice and all, but normally your components or your software components are not that easy. Normally you have in a component one part that is your public API that you want to make official to the world, but maybe there are other things where you say, no, I do not want that this is actually accessible from the outside. Yeah, and this is why there's also an extended component which is called component with interface, where you can actually have this. You can have a private part of your component and a publicly accessible path. You can say, well, in C++, I have my public and my private and protected, but this is a little bit different, yeah, because this is now on the API level. Yeah, you still have to have often some kind of restriction, what kind of internals you can actually use and what not. There are different criteria to do that. And what you can do in this small architecture as code approach that we're presenting here is you can say, I add a mapping to a component. In this case, it's the component hardware. And everything is actually private. So you have this addition here. Yeah, everything, nothing can be accessed from here actually. But you can access only, there's one exception, you can, for example, access this header, everything that is in this header. Yeah, this is my public header. This is a very C-like example, but it translates smoothly also into C++, believe me. Yeah. So this is like now a refinement of this component. And now we actually have something like this. It looks already quite complicated. You do not have to draw this. So this is actually, again, generated. But you see hardware is now split on. We have an interface here, and we have an implementation part. And you see here only this interface part. Do not mind about the symbol. The symbol doesn't matter. Yeah, but these actually accesses, engine controller, I/O, and sensor, they can only access this interface part. And we know due to the mapping, this is actually this one header file. Yeah, and the rest is hidden, and nobody can access it from the outside. So this is the perfect world we would like to have. Yeah, and we think is true for this project. Yeah, and actually the nice thing is now with this this code to architecture approach, this can again also be generated. And what you can see here now, you see here in the middle the code model, you see here the architecture model, and these blue arrows, these are actually this mapping. Yeah, it says, for example, here hardware is mapped to this internal stuff, but the hardware public header here is mapped to the interface. This is what we want. And this can be now generated automatically. Okay, now let's go to the actual, now we have everything. Now we have all our three things. Now we have to put it into the oven and wait for the results, yeah? And the oven is what is called the architecture check, yeah? So now we actually can provide this code model, the architecture, and this mapping to a special algorithm that computes now possible deviations, what already Daniel mentioned in one of his first slides. And the idea is now, we start with all the elements that are in the code model. Yeah, for example, here we have a function, and here we have another function, and this function, for example, calls this one. And we see here this function is mapped to B, and this function is mapped to C. But you see in the architecture, B is allowed to depend on things from C. So great, wonderful. Yeah, this is beautiful. This is how this actually should be used. So we just say this is a convergence and say, great, this is fine. But of course, you know, the world would be boring if there are only convergences. Now, let's take a look at this edge. And now I think you see already the twist. We again say, well, this actually is mapped to B, and this is mapped to A. We have a connection between A and B, but it's the wrong direction. Yeah, so it has to be from B to A. It's not the same way around. Yeah, because somehow this is a middle layer. You do not want to have something back here, for example. This means this is a violation. Yeah, you want to have something like this. This is the code actually does not correspond to what is happening in the architecture. This is what we call a divergence, and this is what normally is reported. Yeah, this is what is interesting. As Daniel already mentioned, it could be that the code is wrong. It could be that the model is wrong. Yeah, we do not know. We just report this is a divergence, something bad. Okay, but there's one thing more. Maybe if you look at this, would you say there's something else fishy in here? Is there something what you say where we would say maybe this is strange why something is here? If you look at the architecture model, and let's say this is everything that's happening in the code, nothing else. Yeah, what would you say? Very, very good. There is one missing, so to speak, in the code, actually, because we say here A depends on B, but it does not depend on it. Yeah. So there is nothing. A does not need B. Why is it here? Yeah. Again, the question is, what is happening here? Is there something wrong in the code? Did somebody forget to call B? Yeah. And now everything goes explodes. Or is there actually A does not need B? Maybe it has required it a long time ago, but now it does no longer need it because it did some changes. We have seen the example from Daniel before. Yeah. So this is also something which is interesting to know, but it's not that normally not that critical because sometimes it's also the case that you have one architecture for multiple projects, and sometimes it's the case that, for example, my car does not have a clock. I'm quite sure it has one, but I do not have a clock in my dashboard. Yeah, it's a very, very easy dashboard, but I'm sure the functionality is there, but it's not used in some way. So maybe there is an edge in the architecture, but not in my product variant. So what this is called is normally an absence. Yeah, and this is also something that you have to think about. How would you like to deal with this in your architecture? Is this really a problem, or is this something you would like to get rid of? There are ways of actually dealing with these absences. If you're interested, we can talk about this then later on. Yeah, but these are the two things that normally are reported: absences and divergences. So the idea is now, as I said, we have now our beautiful model here, and you do not know the source code. It's not your code. It's our code. So we just put it into the oven, and what we get now is something like this. This looks quite interesting. Yeah, it's always good to have some red edges here because, as you remember, red means divergence. Yeah, so we have a lot of stuff what is going on here and what is actually wrong. Of course, this is a training example. Yeah, but let's just pick one of this. This one is interesting. How can we interpret this? We have this sensor component, and we have actually an edge that goes to this implementation part. You remember from before, we have split this hardware part into these two parts, into an interface and into this private part, this implementation part. And something is going on here. You see, actually, there is a divergence that goes to this, but actually there is a dependency from sensor to this interface. But somehow this interface is not used. So there's something fishy going on. Yeah. So we see this here in a small excerpt over there. Yeah. And if you want to know what actually happens there, if you use, there is, of course, tool support for that if you're interested. For example, this is a screenshot of one of our web interfaces, IDEs, where you see exactly what's going on in the code. On the left side, you see the source of the violation. Yeah. You see here there's an int overheated function. And there, return get temperature. You see here, we come back to the beginning, yeah? Get temperature is greater than 42. 32 was it, but whatever, yeah? So there's something like this. 42 is always better. And on the right side, we see actually this get temperature thingy is in the hardware internal header, yeah? It's actually declared in there, yeah? So this is something that looks fishy. Somehow the developer of this hardware component that didn't want to expose this, but somehow one of the colleagues just exposed it anyway and used it in another component, which is bad. Yeah, so this is really bad because the temperature might now be Celsius again. Yeah, and there is not this middle layer that is done. Yeah, and is actually used as it should be. And you see here, this is how you can now really discuss about architecture. You can see this is happening. This is the proof. You have it here. And you can actually talk about it, for example, in the next review, yeah, and see what is happening here. And of course, avoid that things like we've seen before actually happen, yeah, because you can now analyze this and fix the problem accordingly. Good. Just a small word, if you're interested in this and say, well, yeah, this is kind of interesting to have this now we know how this is modeled, but how can we use it? The thing is now, you should, as already mentioned, put your architecture information. The best is to have it actually in your source code. You can have it in other ways, but this is a very good thing. Maybe for every component, have a small architecture description. Start high level. Yeah, don't do too much, but start with a high level architecture. It already helps a lot. I think I can really here say this with confidence. and use this in version control so that it is really at the side of the developer, and the developer can look at it. It doesn't have to have another tool. He can have it. A lot of people are happy with it, but we also saw a lot of teams that actually are happy having this in a text format in their own IDE, and maintain it. The idea is now, if you have a static analysis tool running, like the Experience Suite, you can use this in your continuous analysis. So the code with the version control system, you get a state of the code and of the architecture. You build this information that we have seen, the code view and the architecture view, and you do this analysis. You put it into the oven, and you get architecture check results, as we've seen in the last slide. You can inspect them in your web UI or in IDE plugins, or also use our modeler if you're interested in that. And then, of course, you have to discuss it. This is important. The discussion has to take place if there is something unclear about an architecture violation. To see, is it a code? Is it a model? Is it something else? You have modifications, and then, of course, the cycle of continuous improvement starts again. And hopefully, in the next iteration, there are less architecture violations. As such. Good. And I would say, as a small summary, really, let's take it brief. So what we would wanted to do with this talk is to show you the basics of architecture verification, what it actually is, and how you can use static analysis information to verify your architecture. And as a kind of a special case here, we looked at architecture as code, this very lightweight modeling approach that does not need too many additional models and things in other tools. Where you can use, for example, such a Python DSL. I just have to, for completeness, say here, you can also use C4. You can use planned UML, etc. So it's normally possible to have these lightweight models also imported into the actual verification approach. And but what is the nice thing here? We have seen this with the mapping. This approach, if you use this Python DSL approach with this framework that we introduced, you have actually, this is very good for automated verification, because you can, for example, provide also the mapping. And you can use this data very smoothly within the analysis framework that, for example, the Experience Suite offers. Good. I think we are way too fast, but maybe this is not necessarily a bad thing. So thanks a lot. And if there are any questions.